Russell Engelman, thanks so much for coming on to Evolution Soup, all the way from Cleveland, Ohio. You are a PhD student in the Department of Biology at Case Western Reserve University, with interests ranging from dinosaurs to extinct marsupials. This year you published a paper on Dunkleosteus, the most famous of all the armored fossil fish, with new findings that surprised everyone, including yourself. Welcome to the show, Russell. Well, your research has certainly made a splash in the paleo community, so how has your paper been received?
Well, I think it takes time for people to digest and process any new research, but based on the reactions I've gotten from talking to other placoderm specialists, I think the reaction has been mostly positive.
Well, before we dive into the world of Dunkleosteus, let's just hear a little bit about your background. Russell, where did you grow up, and did you always have an interest in ancient animals, and, in particular, ancient fish?
So, I'm actually from Cleveland, Ohio, so I pretty much grew up with Dunkleosteus all my life. I've been interested in fossils ever since I was less than 1 year old, and I pretty much always wanted to become a paleontologist, and that's part of the reason I eventually ended up at Case Western Reserve University. However, most of my previous research experience hasn't been with fish. It's actually been with mammals. I knew about Dunkleosteus, and I knew some stuff about fossil fishes and living fishes based on just growing up around the area. But at the same time, most of my research prior to this point has been focusing on fossil mammals. And most of what happened is during COVID, our lab group couldn't go to do research on the fossil mammals we usually went to, so I decided to do some projects that were closer to home.
Well, let's begin with some background on this animal and the period of time in which it lived. Dunkleosteus was an armored fish, part of a group called the Placoderms. Russell, what exactly is a placoderm?
So the placoderms are this group of extinct armored fish, which are mostly restricted to this interval of time called the Devonian period. This is a 60 million year span that ranges from about 420 million years ago to about 360. And during this point, the placoderms were incredibly diverse and occupied all sorts of different niches. There are many different groups out there. Specifically, placoderms are jawed vertebrates, and they're thought to be some of the first jawed vertebrates. There's actually kind of a debate going on over whether placoderm is a useful term, because there seems to be certain placoderms, specifically the maxillate placoderms, which are more closely related to the later jawed vertebrates than they are to other placoderms. And there's other debates if, say, the group that Dunkleosteus belongs to is more closely related to modern vertebrates than it is to some of these other placoderm groups like Bothrioplepis and the Antiarchs. So the placoderms are notable in that they're the first vertebrates with jaws, but they don't have teeth in the way that we think of them. They actually do have teeth. It's kind of a misnomer, but their teeth are kind of fused to the jaw. They don't have any enamel or dentine or things that we'd really recognize as teeth. And realistically, in a lot of these species, the jaws actually form the shearing edges rather than the teeth being used to grab and snag food. The placoderms are almost completely restricted to this period called the Devonian period, as mentioned before. This was a period that's called the Age of Fishes because this is the point in history when fishes really started explosively diversifying. Prior to the Devonian, the oceans tend to be very heavily dominated by invertebrate faunas, mostly cephalopods, trilobites, giant sea scorpions, and there were some groups of jawless fishes. But during the Devonian, there's this huge explosion in diversity. The Devonian is often talked about a lot in terms of this is the time of the, quote, conquest of the land. This is when plants moved onto land. This is when trees first evolved. This is when insects started moving onto land. The Silurian, this happens a bit too, but the Devonian often gets pigeonholed as this period. And the Devonian is also when the first four-limbed tetrapods come onto the scene. What a lot of people don't know is at the same time, there's kind of this expansion and increasing complexity of marine ecosystems. You get a lot of organisms, like before, marine life was mostly concentrated along the continental shelves, and most of it was concentrated close to the bottom. The Devonian is the point in time in which you get a lot of free swimming animals that are just lifting off the seafloor. This is when you get like the first free swimming fishes mostly. And at the same time, you get this expansion of freshwater ecosystems as plants move inland. They change the freshwater ecosystems to become more complex. You get the first what you'd call like a modern river ecosystem. You get the first open ocean faunas. You get the first possibly you get a lot of these ecological niches that we think of as just typical to modern oceans, but they didn't really exist prior to the Devonian.
And you said, Russell, that they existed in the Silurian in the era before. Is that right?
A little bit. The issue is the Silurian fossil record isn't great. We have some evidence of early placoderms and some of these other groups of fishes from the very late Silurian. The issue is that the Silurian as a period is not very well characterized. I've heard other Paleozoic paleontologists describe it as basically it's just a prologue to the Devonian, which is probably not fair to the Silurian, but it does describe kind of what our current knowledge of the Silurian is.
Russell, can you give us a detailed overview of Dunkleosteus?
Dunkleosteus is perhaps one of the largest placoderms, and it's one of the largest animals in the Devonian, and even with this new research, that really hasn't changed. Dunkleosteus is this very large predatory placoderm that's known from the last 2 to 6 million years right before the end of the Devonian period. And this animal was found, the first fossils were found in Ohio, and this animal is thought to have probably been the apex predator of the Devonian oceans. This is an animal that has a head and part of the torso are covered with armor, but the rest of the animal would have had a body that is kind of shark-like, but also has some similarities to tuna or catfish, especially in the skin texture. So they're not really scaly animals. So the first Dunkleosteus fossils were found in Cleveland, and it's always been recognized that these things were large predatory animals. There's been a lot of different interpretations as to what they looked like. The initial describers thought they were giant lungfish. So there had been a spate of research on them. There's quite a few papers going from about like 1860s to like 1930s. And the big problem is that the research stopped right about the same time as the first complete specimens came out of the Cleveland Shale. But the thing is that those complete specimens, due to a fluke of history, ended up pretty much not getting described. So the last description of Dunkleosteus that was really extensive was in 1932, and it didn't even take into account all of the fossil data that we had at hand. So other specimens of Dunkleosteus have been found worldwide. There's some from Morocco, there's some from Poland, there's some from other parts of North America, but they're mostly just fragmentary bone chunks. It's likely that probably fossil collecting in other parts of the world are going to turn up more specimens. Dunkleosteus has always been this weird blank spot in paleontology for several reasons. Probably the most immediate reason is that Dunkleosteus has a head and a shoulder girdle composed of bone, but then the rest of the animal's body was more or less composed of cartilage. There may have been a very thin layer of perichondral bone covering most of the skeleton, but that almost never preserves. So what happens is that very often we get the armors of Dunkleosteus, so we know what the head looks like, but anything behind the head is very, very hard to puzzle out. We do get other placoderms for which we have complete body parts, and we can kind of piece together what the body looks like from that. But this gets us to the other issue in that Dunkleosteus basically hasn't really been touched as an object of study for a very long time. Now, to be fair, there were a series of papers that were published on the jaw mechanics of Dunkleosteus. That's the suction-feeding bite force papers a lot of people like to refer to. There was a paper on the general paleobiology of Dunkleosteus published in 2010, and then there was a paper published in 2017 that looked at trying to back calculate tail fin shape in Dunkleosteus. But really, other than those papers, the last real publication of Dunkleosteus that looked at the bones and the anatomy was back in 1932. And we've learned so much more about placoderms since then. People have found complete skeletons. We found these beautifully preserved 3D fossils in the Gogo Formation. There is that recent discovery of a very pelagic adapted placoderm last year. And no one's actually gone back and taking another look at Dunkleosteus based on this data. And it shows. So in the 1930s, and this is part of the old idea that a lot of late 19th, 20th century scientists had, that anything in the fossil record was slow, sluggish, and primitive. There's a really good quote to Newberry that kind of sums this up very well. Dunkleosteus was seen as a big, slow, poorly adapted animal that was basically just a seat warmer until sharks got going and forced it out of that niche. And pretty much what we've been finding is that this probably isn't the case. It's more based on initial assumptions, but because no one actually went back and looked at Dunkleosteus, revised it based on what we know now, well, that old depiction has continued. It's been continuing even into the early 20th century. Like, most of the depictions you see of Dunkleosteus are based on these older 1930s depictions, even though even among scientists there have been more up-to-date depictions that were made in like the 90s and the early 2000s. They weren't like major published papers, but like there were some suspicions that they were a bit like not as slow and sluggish as was depicted.
So it sounds like what you're saying, Russell, is that they've just been a big scary head in the museums for all this time, and not much description being done on them.
That's about it. This is something I've really noticed, is that Dunkleosteus gets shown in a lot of museums, and it's almost always the exact same specimen. It's a cast of this one from Cleveland, CMNH 5768. And this specimen gets shown as this big, scary trophy head, like how you'd have like an elephant head or a lion head mounted over a mantelpiece. But when you actually look into it and you look into what the actual science behind this animal is, there really isn't a lot. Like, if you compare the amount of research on, Tyrannosaurus rex or Smilodon or Triceratops or any of these other big-name paleontological phenomena to Dunkleosteus, there's almost nothing on Dunkleosteus. The only animal that's as understudied, I would say, and is also like a household paleontological name, is Dimetrodon. So again, like I started this thinking there was a lot more information than there was, and I started digging into this, and I found like there was not much at all. Like, even these very basic questions about Dunkleosteus, just no one had tried to even ask. Or if you want an even better comparison, compare Dunkleosteus to Megalodon. So think of Megalodon this way. In the last 10 years, it almost feels like there's been 1 to 2 studies out on Megalodon every year that are trying to find some new aspect of its paleobiology based on what amounts to a bunch of teeth and a handful of vertebral fragments. Dunkleosteus, we have quite a bit more, and it's just, again, not touched. It's kind of like this massive blank space. And I think a lot of this is people assume Dunkleosteus has been studied to death. And I've had people even tell me this, say, like, I thought there were like umpteen billion papers of Dunkleosteus, and it turns out there really hasn't been.
Well, there have been plenty of depictions of Dunkleosteus over the decades, where all manner of shapes and sizes have been presented to the world. Plenty is known about the head, but nothing at all really about the rest of the body. Before we get into your discoveries, can you tell us why you decided to take on this research?
So, like I said before, COVID had prevented my lab group from doing the typical research that we did on South American fossil mammals. So, I decided that I would do what I had always wanted to do for a very long time, and I would go poke around with the Cleveland Shale fishes and see what I could find. I had some ideas for projects I wanted to do, and another thing, and I also wanted to promote the fossil finds of the Cleveland Museum and the local holdings, which, even in like Paleozoic fish paleontology, kind of get treated like this massive blank spot. Like, even major reviews of Paleozoic fish paleontology just kind of say, "Oh, here's Dunkleosteus. It's a big scary fish. Moving on." So I wanted to look at these things from more of a paleobiology, paleoecology perspective, because that's always what's interested me as a scientist, and that's something that I thought that the Cleveland Shale fishes really needed. They needed more of to be looked at from an ecological perspective as opposed to just describing the fossils. So I went into the collection of the Cleveland Shale, and one of the things I had to do to work on these fish is I needed an estimate of body size. Because, as many scientists have said before me, nothing in biology makes sense without body size, and it's probably the single most important variable that affects the biology of an organism. Just as a simple example, if I wanted to compare features between two species, and I want to say, oh, this one has a big jaw and this one has a little jaw, well, you have to know how big they are in order to scale those jaws next to each other. So again, size determines quite a bit. So I went in, and originally what I was doing is I used the methodology of the previous studies that had calculated the size of Dunkleosteus, and I thought I'd just apply those to other fish. And I started working with them, and I found that the values didn't make any sense. They were very confusing. I remember looking at some of these specimens that they were claiming they had calculated lengths of like 5-7 meters. And these were specimens that like the whole thing was maybe this big. They were not huge. They were not huge specimens. And that really got me wondering, like, is this method even reliable for these placoderms like Dunkleosteus? So I had to put the other paleobiology products to the side because those didn't work unless I had size estimates for these species. And I decided to go back and see if there was any way to double check these size estimates with Dunkleosteus. And what I really found is that like the methods that had been proposed for size estimates really they didn't work. So what I did is there are these smaller placoderms. There's like Cacosteus is the one everyone thinks of. There's like a handful of other ones. And I took these methods and I said, okay, what happens if we apply them to a placoderm which we know how long they are, so we can figure out how accurate this method is. And it turned out this method was extremely inaccurate. It basically had an error of like almost 50 to 100%. So I had to think about this, and I basically had to think, okay, what can I actually use given this very limited fossil evidence that I have with Dunkleosteus to get a ballpark estimate of size? Other authors had suggested that brain case size is pretty constrained in animals, and gill chamber size in fish specifically is also expected to be fairly well constrained. So maybe that region can work. So I kind of did this measurement that had been somewhat applied to mammals in the past. I later found out that they'd applied it to like crocodile line archosaurs, and it's also kind of worked. So I modified it and I applied something like that to fishes. And I originally I did this as a reality check. My thought was, okay, so I have these measurements from the mouth, which that's the previous way these size estimates were made, and I have these estimates from the head. And as long as they're relatively similar, I can say, okay, the mouth is close enough. I'll just go with the mouth estimates. And it turned out that the head estimates were like half of that of the mouth estimates, and I was like, oh my god, like what is going on here? So I thought, okay, maybe the head estimate's wrong and these things just have little tiny pinheads or something. So what I did is I got a broader sample of placoderms and living fish, and this wasn't the big one I used for the paper, this was just a test sample, and I ran it, and it's like, oh, mouth size doesn't correlate with body size, but head size seems to correlate pretty well. But the thing is, when I ran the head size, I started getting links of like 3.5 meters, 4 meters for these specimens, which were a lot smaller than people had been saying.
So, what exactly was the methodology that you used to find the body length of Dunkleosteus, and did you have any expectations at all?
I had no expectations at all going into this. Honestly, if I had expectations, I pretty much thought I was just going to go into this and independently validate these 7 to 9 meter estimates that have been always thrown around for Dunkleosteus. So to test this, what I did is I measured what I've been calling orbitopercular length. That sounds a bit complicated, and I sometimes think that the wording maybe I made it a bit too complicated. Really, all it is, it's just head length and then without the snout length. Because the back parts of the head, the parts that contain the brain case and the gill chamber, are pretty rigorously, or thought like theoretically they'd be expected to be pretty well constrained across fishes. Specifically, an animal is not going to have a brain that's supremely huge or extremely tiny relative to body size, or else it can't function. There are exceptions, but The brain case in other groups has been shown to be relatively okay at estimating body size. And then the gills are constrained how big or small they can be, because if an animal has gills that are too large relative to its needs as an organism, they're just kind of useless. And if they're too small, the animal instantly suffocates and dies. So, and the reason I excluded snout length was that the snout is more variable due to ecology. A good example of this is like compare the skulls of a wolf and a cat. They can have very similar neurocranial links that's roughly equivalent to OL, sort of, but then the wolf has a very, very long snout and the cat doesn't. The other thing I found out as well is that placoderms have systematically shorter snouts than other fishes. So if I just used head length by itself, that's actually unfair to placoderms because that gives you a length of like 2.7 to 3 meters for Dunkleosteus. It makes it a lot smaller than even I predicted. So in order to make things fair when comparing placoderms to non-placoderms, I use this length of the head length minus the snout. And so what I did is I got the initial results back, and they were saying like 3.5 to 4 meters, and that sounded wacky to me because like no one had ever suggested they were this small before. That sounded very strange. So what I did is I tested this method a lot of different ways. I did all these different variations. Like I said, okay, what if we only look at open ocean fish? Do the results change? No. What happens if we only look at sharks? Because sharks are thought to be similar to arthrodires in a lot of ways. It doesn't change, and actually it makes the animal shorter. I tried numerous different methods. I accounted for lots of different variables, and every single one gave me links of like 3 to 3.8 meters. In fact, the links that I reported as the best guess are kind of on the high side for the estimates I'm getting. I think those are probably right based on the other proportions, and that gives me to the other thing is I thought, okay, this one method gives this. Let's test this in some other way. And I got some other methods of testing this. I looked at where the pelvis approximately is in these species. We can kind of figure that out. I scaled the length of Dunkleosteus using the linear measurements of various armor plates, and all of those gave the same length estimates. And that was actually very surprising because people had often implied that they took armor plate measurements from these smaller placoderms and then scaled them up to Dunkleosteus to get these measurements. I don't think they did, because when I did the same thing, and I used some of the largest Dunkleosteus specimens we know of, I still got lengths of only about like 3.4 to 3.8 meters. And so what happened is I actually went back to the literature and tried to figure out where are these larger estimates coming from. And I think there's a couple interesting things there. One of which is that other than this 2017 study, which is one of the first attempts that anyone really did to get a quantifiable estimate of Dunkleosteus, there's been like maybe one study that tried to quantitatively estimate the size of Dunkleosteus. The other estimates all seem to be mostly speculative guesstimates that probably started back with like Newberry's initial description back in like 1879 before he even had a complete specimen. And then people have just been repeating them ever since. And there's another thing that happened related to this. There was a typo in this famous paleontology textbook where the head of Dunkleosteus was basically described as being 2 to 3 times bigger than the specimens actually are. Like they were bigger than the biggest specimens I've ever seen. And I'm pretty sure that people repeating that typo over and over again is where you're getting these citations of like 9 to 10 meters for Dunkleosteus. And again, because no one has looked at Dunkleosteus from an anatomical, comparative, or quantitative perspective before, like not before, but since the initial spade discoveries in the 1930s, or at least no one's published on it. If someone has, I'm not aware of any such papers. These results just kept being repeated over and over again, and nobody actually checked because everyone thought Dunkleosteus was well studied.
Right. So what does this mean for Dunkleosteus as a predator?
Even though I know a lot of people have been disappointed by the shrinking of the size, this is actually kind of an upgrade for Dunkleosteus. So before, there's always been this thought that Dunkleosteus was this sluggish, lumbering, primeval sea leviathan. And you still see this in a lot of depictions. Again, like Newberry, even back his original description, kind of described it as such. Other authors kind of said this. But what we're getting from this, and what we're getting from other discoveries on placoderms, is that these were much more active animals than we had thought. These were fast-moving predators. And with Dunkleosteus specifically, the body shape that seems to be coming out of it, based on the dimensions of the trunk armor, they look a lot more almost like tuna than they do like many of the other fishes that you see in the oceans today. Like, even if you mess with the dimension of the armor to account for various things, like, there's almost no way to not get this deeper tuna-like body shape. And that suggests that these were very fast, active pelagic fishes, which, to be fair, people had been suggesting this for years. Carr had been suggesting this. Farron had suggested this. But this and some other data that's still being worked on is suggesting that these were probably very active animals, probably similar to modern great white sharks or modern tuna, and probably very fast, surprisingly. And I would almost say this is like, not this in particular, but like some of the stuff we're getting out of placoderms in general is kind of akin to like dinosaurs pre and post Jurassic Park, where pre Jurassic Park they were thought of as like, and pre dinosaur renaissance, I guess, they were thought of as these lumbering, tail dragging reptiles. But as we do more research on them, we find that they're active animals. They're really well put together, despite being so big, and that they're much more active, dynamic animals than we've been giving them credit for. And again, this goes back to the initial presumptions of, oh, they're extinct, they must not have worked very well. It turns out they worked out very well. It's just that they had the very bad luck of going through the Devonian extinction. And even though these estimates are smaller, I also went through and looked at like the size of some of these other species. Dunkleosteus was still probably one of the largest predatory fish species that existed up to that time. The only fish that may have gotten larger on a consistent basis is this giant filter-feeding cousin of it called Titanichthyes. But like, we have other fish from the Devonian, and all of them seem to max out at about the same size we get for the largest Dunkleosteus. So there's a pretty good congruence that in the Devonian, like a size of maybe 4 to 4.5 meters was the largest vertebrate to have ever existed on Earth up to that point.
Well, no matter what the size, Russell, if I always say, if you saw that face coming at you underwater, with that set of jaws there, that would still make it the most badass thing out there, I think.
Oh, definitely, especially because based on some of this research, it'd be coming at you a lot faster. Like, it'd be scary if it was coming at you, but you might not even see it coming. It might be like, what you see with some of these tunas or great white sharks, where they just ambush their prey, and all of a sudden it just drives by you and you're missing a third of your torso.
Well, Dunkleosteus eventually disappeared from the world, as did all of the placoderms. So what exactly happened? Do we have any ideas as to why these animals went extinct?
So Dunkleosteus went extinct in the Hongenberg event. This is the second of the two-part Devonian extinction. The Devonian extinction and its causes are still debated a bit. They're not as heavily nailed down as like the Permian extinction or the Cretaceous extinction, but the evidence is starting to shape up to suggest that more or less trees murdered everything. Specifically, trees evolved for the first time in the latter half of the Devonian period. And when they did, they caused massive changes to the Earth's biochemistry. Specifically, they increased weathering due to their roots, and they changed the banks of the rivers due to their roots, and this caused even further weathering. This caused large amounts of sediment load, which would have drifted down and smothered the estuaries and the coastal regions, that's where most life existed during the Devonian. And on top of that, the trees would have caused this mass drawdown in carbon dioxide just by existing. So on the one hand, you have this massive increase in biomass on the land where there pretty much wasn't anything before. So think of all that carbon dioxide being sucked out of the atmosphere and formed into tree biomass. Then on top of that, the roots exposed more silicate minerals. And when silicate minerals weather, they suck more carbon dioxide out of the atmosphere. And together, this caused what amounted to a snap ice age. And you can actually see this in the sediments. There is evidence of glacial drop stones in the Cleveland Shale south of where we find Dunkleosteus. And these are stones that had to have been dragged into the ocean by glaciers, except the only problem is that these sites would have been at the latitude of the Bahamas at the time that these things had formed. So really, this would only happen if something had gone very, very wrong with the ecosystem. The Devonian extinction is actually very important, not just for its effects, just, okay, it killed off Dunkleosteus. I find the Devonian extinction very interesting because this is an extinction which we are pretty certain had a cause that an organism did this, as opposed to, like, massive volcanic eruptions or space rock. And with regards to, like, modern issues with human caused habitat degradation and fossil fuels, the Devonian extinction seems like it's pretty relevant for issues today.
Well, it's very important work that you're doing, Russell, and one of the most fascinating prehistoric animals out there, and definitely a great favorite of many of the Evolution Soup audience. So, what are you working on at the moment? Any future projects you can tell us about?
So the big project I'm trying to get done is the third part of my Dunkleosteus studies. I had 2 papers come out. So I had this talk at SVP, and the research that was at that talk has been split into 3 papers. 2 of them have come out. One was reevaluating the old length estimates. The second was proposing the new length estimates and the evidence why. And the third is I wanted to do a paper describing the comparative evidence. Basically, what do we know about what Dunkleosteus looked like? Because the fact is, even though we're missing the back half of the animal, we can actually figure out quite a bit about what the back half should look like, just based on comparisons with other placoderms, looking at the bones of Dunkleosteus, or just broader, like, biomechanical patterns that we see in fishes. So there are anatomical reasons that the recent reconstruction looks the way it does. It's been revised slightly, but I want to get that evidence out there into the scientific literature. So that's the big thing I'm working on right now. Other than that, I'm still working with my lab group. We're still doing research on South American mammals, and one of which is it's my PhD research. I have to get that done. It's doing some work with comparing South American mammals with those on other continents, as well as there is some research working on, like, broader patterns in the evolution of South American endemic ungulates.
Russell Engelman, thank you very much indeed.
Thank you very much. It was very nice to be on.